background independence. So that's related but not quite the same. It means that one doesn't start with a formalism where a priori a particular metric would be distinguished. Of course, when I set up perturbation theory around Minkowski space, then this Minkowski space appears already a priori as kind of a chosen, a choice I have made. And of course, I will have then to, if I want to generalize it, I have to trace back how the dependence on this specific kind of background structure influences the results of the quantization. So by background independence, one also means typically that one doesn't want to make any specific choice of any distinguished metric. And of course, we'll come to the path integral, but this then typically means that you are going to sum over all geometries, say, over all four-dimensional curved geometries in the path integral, without singling out any particular one as being special a priori. But the idea is that the dynamics, the quantum dynamics you're defining, should then dictate kind of what are special metrics. I mean, what are then solutions, say, to your quantum equations of motion? And in this way, well, there will be a result. There will be maybe one or several distinguished space-time metrics to come out as a result of the dynamics. But you're not putting it kind of in by hand at any stage. Of course, none of these properties are properties that are forced on you. So in principle, a priori, it could have well been the case that this perturbative procedure led to a sensibly, to an interesting and finite result, say. But, well, it just happens to be not the case. So it's not that one necessarily has to go wrong if one quantizes perturbatively or distinguishes some a priori metric. I mean, that's not the case. But of course, if you see that when making these choices, you are going wrong in some way, you might want to consider alternatives. I also then said, well, there are basically two distinct ways of going about constructing a quantum theory. And they are, in principle, they're equivalent, but they look sufficiently different, certainly at an intermediate stage, in terms of the basic ingredients you're working with, and we kind of to merit a separate discussion. And those two choices are kind of the Hamiltonian way of quantizing, I mean, based on a classical Hamiltonian formulation, and then there's a path integral of quantizing based on the action and classical action principle. So we're getting started with doing things the canonical way. And I reminded you briefly yesterday about some essential structure underlying classical Hamiltonian dynamics of a simple finite dimensional system. And of course, for the field theoretic case we're interested in, this will be an infinite dimensional generalization of what we're doing here. So I'll continue doing a little bit of this today. So that was what we started out discussing yesterday. How is classical dynamics formulated on a phase space? And the phase space, in mathematical terms, well, it's usually taken to be a differentiable manifold with an extra structure on it, a symplectic form or symplectic structure. And sometimes this is called omega, and then this was the symbol I used for the phase space, and then omega is a symplectic form. You can think of that as just being the Poisson brackets. But of course, you can think of it in various equivalent ways. You can also think of it as kind of a two-tensor, which takes kind of two vector fields. These are the Hamiltonian vector fields associated with two given functions, and spits out a number. And that number, or a function, that would be the same as the result of the Poisson bracket of the two functions, phase-space functions you started with. But I don't want to go at all into the mathematical niceties of this classical formalism. Just if you have heard about this more mathematical way of speaking about this, well, here, this is what I have in mind. Now, what we said is that so the presence of the symplectic structure, omega, the Poisson brackets, gives, of course, an additional algebraic, provides us with an additional algebraic structure, which we might wish to preserve, well, as much as we can in the quantum theory. There was also a general question that came, someone came with after the lecture. I mean, how am I supposed to think of this, quantum theory thing? I mean, the way I'm presenting is, we are looking perhaps for associating a quantum theory with a given classical theory. But this inverts a little bit how we really think about the physics. I mean, we are thinking of quantum theory as something more fundamental, whereas here, of course, well, practically, one is often forced to taking the opposite point of view, starting with a classical, at least say for the case of gravity, with a classical theory we are well familiar with, and then asking, well, which quantum theory could have that as its classical limit? So in a way, your starting point is then the kind of the classical theory, and you're thinking of some kind of, mapping, like what I was writing down yesterday about the quantization map, to map that into a quantum theory. Well, that's inverting the logic a little bit, but it's certainly a practical point of view, and I would say certainly for the perturbative quantizations, well, that has turned out to be a very fruitful way of thinking about it. Think about the quantization of electrodynamics. Of course, what the question is, well, is this a unique association? And already yesterday, the results I quoted to you said, well, no. And, well, maybe we would also be surprised if that were so. Then one could really imagine one has, it starts always from classical theories, and one just has, one turns a crank, and out comes, a unique quantum theory. For the case of classical mechanics, in sufficiently simple cases, we were actually lucky, and that was the contents of the kind of uniqueness of the Schrödinger, the representation of kind of the Schrödinger type representation of the canonical Poisson brackets. So let me remind you. Let me just write this down briefly. There are various ways of phrasing this. So that concerns the simple case of quantum mechanics on Rn. That's, of course, what our textbooks, our quantum mechanics textbooks are filled with. And here, this way, of associating the quantization with the classical system worked in the sense that that one can show that there is essentially a unique representation of these classical Poisson brackets. Now, algebraically speaking, they form, together with the unit element, the so-called Heisenberg algebra. So the simplest case is that when I have a single x or q and a single p, plus the unit element, because why do I need the unit element? Because I had my only non-vanishing Poisson brackets were these delta ij's. Okay, now here I'm assuming already some index that runs from 1 to n, but if n was 1, I have just the smallest Heisenberg algebra is just that of having a single q, a single p, and of course the unit element on the right-hand side. So of course I need to add this. This is part of the algebra, otherwise this thing doesn't close. So of qi, pj, and 1. Now, I also pointed out to you that one usually wants more than just representing the algebra of the fundamental kind of the coordinates on phase space, but certainly one quantity one always wants to quantize is the Hamiltonian. So the Hamiltonian thought of as a function on this phase space here. So I'd better make sure that this can be quantized also. a Hamiltonian. So I would start from some classical object and hope to be able to represent this kind of in a consistent way that is consistent as far as kind of these classical algebraic relations is concerned, to represent this by a self-adjoint operator, which I can then diagonalize in the usual way. Now, in principle, there might be more than one association that is possible here, which then would lead to potentially physically inequivalent Hamiltonians. Well, then we won't just scratch our heads, but then we would say, okay, look, I have two different predictions for possible quantum theories, and look, they lead to two different Hamiltonian operators with these different spectra. Let me go out and measure in nature which one is the correct one. Or, of course, what also feeds into these issues, if one has kind of more than one associations, are things having to do with boundary conditions typically. But they may not be so obvious. They may not be a totally obvious physical implementation of what you're after. So if any questions arise, you would say, okay, let experiment decide if that is not unique. So this is not the end of the world. A source of non-uniqueness we have already met yesterday came from factor ordering issues. So even if everything here is given in as polynomials, of course it might be an infinite sum of polynomials, even if that is the case, you immediately run into ordering problems if you represent those by self-adjoint operators, because then qi hat and pi hat no longer commute and will in general just, well, they just correspond then to different quantum operators. And of course the same holds for higher order polynomials. And this is something that cannot be fixed by a general prescription. So there are ambiguities there, which maybe let one renormalize already one's expectations of what one might be able to do in terms of having very general prescriptions. You know, you give me an arbitrary classical system, and I give you kind of a corresponding quantum system. That tends to become very quickly very involved. One source is when this space is no longer a linear space, say even in finite dimensions. Well, that could have various origins. I mean, either that, say, already the space of configurations has some compact directions, that of course sometimes happens, or that is a more usual situation. There is a kind of a gauge symmetry acting on this originally linear space such that the physical configurations are constrained to a subspace of your original space, and that subspace is very often then a nonlinear space. And in that case, well, if that is nonlinear, then actually the Stone-Neumann theorem no longer applies, because you don't have global coordinates on such a space by necessity. I mean, if I have a sphere, right, say a two-sphere, I cannot cover it in a one-to-one manner smoothly by coordinates, kind of QIs. So I always have to be careful in, you know, choosing patches, etc. But how such a procedure translates in the quantum theory is a priori far from clear. It just makes it clear that the standard Schrödinger representation often doesn't work, or at least has to be treated with great care. That brings us to the topic of gauge invariance, and that translates to these Hamiltonian systems under the name of constrained systems. And why this name comes about, what a constraint is, a constraint will be exactly a condition that confines you to a subspace of your total phase space, bringing with it complications of the type I just mentioned. So this goes by the name of constrained Hamiltonian systems. So this comes, this comes up here in passing. It's a genuinely important subject generically. So if you analyze any kind of quantum field theories, and you want, for instance, to understand what are the physical degrees of freedom, you usually do that in a canonical formulation, and you run through some kind of constraint analysis of the type I'll be introducing to you today. So it keeps coming back. I mean, being familiar with this is absolutely essential in many contexts to understand what's the true, even classically, what's the true physical degrees of freedom of any given theory are, for which you just say write down the Lagrangian and the field content. Okay, now, what is my starting point here? For simplicity, we stay, again, in finite dimensions. We look at a Lagrangian system to start with n degrees of freedom. So, an n-dimensional Lagrangian system so think of it as n, QIs, some configuration variables. And now we're looking at a particular subclass of such systems, which are called singular. Now, how is singularity defined here? It's defined by the vanishing of a particular determinant, which I call capital W, ij, where Wij is the matrix of second partial derivative of that Lagrangian with respect to the coordinates q. It is a velocities qi dot. Sorry? Thank you. Yes, I interrupted myself without finishing the equation. Thanks. Right, so the Lagrangian will depend on coordinates and velocities, and typically quadratically. So this is a specific matrix for a specific model. And whenever that has 0 eigenvectors, 0 eigenvalues, then I call the system singular. This here is, by the way, the Hessian of the system, so-called. Now, let me be more precise, and let me look for what the rank of this matrix is. So the rank, of course, now counts, how many 0 eigenvectors there are, and subtracts them. So let me consider the situation where the rank of this W is n minus m, and for the singular case, m is larger than 0. If that is the case, then I have, of course, m 0 eigenvectors. They exist, little m 0 eigenvectors, and let me call them y with a vector index I, and a label which just numbers them from the first to the mth one, subscript little a, multiplied into this matrix gives 0, where a runs from 1 to m. Of course, we are on our way to the Hamiltonian theory. So our next step is to make a Legendre transformation. Now, what goes wrong, in inverted commas, in the situation when my Lagrangian is singular? Let's have a look at this. So a consequence here is that the Legendre transformation, the Legendre transform, of course, which maps me from the space of, could call the tangent bundle, so the space of the coordinates and velocities, to phase space, qi, pi, well, these are either, well, these are coordinates that are globally valid if I'm talking about Rn, but otherwise they're at least locally valid in this manner. This is also singular. Now, why is that so? Because if I now express the determinant of this metric, as I've done here, up there, the matrix of these partial derivatives, of course, I recognize here a single dl by dq dot is, of course, my definition of the conjugate momentum. Right? So this is nothing but del pj by del qi dot. And by my definition of singularity, this vanishes. So you see what happens. You see, this means my coordinate transformation between the velocities and the momenta is singular. Yeah, certainly not. I cannot solve, one for the other. I cannot express all the new momenta as functions of the old velocity. So that's the immediate consequence. We cannot solve. We express all velocities as, well, in a one-to manner, as functions of the coordinates and the momenta. And what this leads to, if you like, what this means is that the Legendre transformation, understood as a map, will only map us onto a submanifold of phase space. So it's not surjective, if you like. So another way of phrasing this is to say that there will be M relations that define then this submanifold. And I'm calling them phi A with that same label A, QP equal to 0. A equal 1 to M. And here I'm making implicitly certain regularity assumptions that these are kind of independent, actually functionally independent expressions. And these are now my so-called constraints. So these reduce you to 2n minus m dimensional subspace of the phase space. So the Legendre transform only goes to the subspace defined by the joint vanishing of these m constraints. So these are the so-called constraints. And of course, we'll have a look in a moment how this affects my description of the dynamics. So I'm just writing this here. So they're assumed independent. So this defines a subspace. So we get a 2n minus m dimensional subspace. And that is called usually the constrained surface. Sorry. So the surface induced by these constraints. Constrained surface. Could call it S, sorry, curly S with a subscript C for constrained. So it's a genuine subspace of my phase space. Okay, let me illustrate this with a very simple example. Then you see quickly kind of what the issue is. So let me just cook up some finite dimensional Lagrangian. 1/2 Q1 dot squared plus some constant C, Q2 dot Q1 minus m/2, a mass term, Q1 squared plus Q2 squared plus Q3 squared. Now, so obviously I have kind of three coordinates, Q1, Q2, and Q3. So 3 degrees of freedom, 3 associated velocities. Now, let me just compute what my conjugate momenta are. P1 is a partial derivative of L with respect to Q1 dot. dQ1 dot is equal to Q1 dot. Now, that's perfectly regular and standard, right? I just express this as a function. The velocity, maybe there should be an m. So, no, there's no m because I didn't put anything here. Okay, P2 is partial derivative of L with respect to Q2 dot. This gives me a C Q1. And lastly, P3 is dL by dQ3 dot. Gives me 0 because it doesn't at all depend on this velocity. Now, you see, well, this is completely regular. Velocity, equal momentum. Here, it's not of the form, because there's not a velocity on the right-hand side. It's just some dependent on the coordinate. And here there's a 0. So both what I get here and what I get here are examples of constraints, right? So there is no, any velocity dependent has dropped out. So I cannot solve for the corresponding, Q dot. And therefore, of course, my omega ij is defined here, or I can just read it off here, has 2 0 eigenvectors. That's the matrix. It's 1 0 0. So it has 2 general directions, and its rank is obviously 1. And the 2 constraints, I just bring them to this form by throwing everything on the left-hand side of the equations. So I have a constraint phi1 given by P2 minus CQ1 equal to 0, and the constraint phi2. So this is just a definition, of course, given by the vanishing of the 3 momentum. And therefore, I read off that my constraint surface is 4-dimensional. Okay. Yeah.
So the way to identify the constraint in local equations just involves coordinate and conjugate momentum.
Yes. Yes. So that's a simple mechanism. I mean, you can, well, immediately read off. This has just a regular dependence on velocity, which is just velocity squared. it's just linear in velocities, well, that's of course, it's not a standard, degree of freedom. And one of the velocities doesn't appear at all, which leads to the presence of these constraints. Yes? Yeah.
So at the beginning, we have coordinates.
Yes.
We look at the tangent bundle with the velocities.
That's right.
So on that manifold, we have to find our Gaussian function, which takes at every point a value. And
that's right.
Legendre transformation transforms
this
only defined on the tangent bundle to function, namely the Hamiltonian defined
yes.
on another manifold, namely the symplectic manifold.
Yes.
And what exactly, how does it look like if the Lagrange
yes.
function on the manifold has a particular setting that this transformation does not work well?
Yes. Yeah, I draw a few pictures, which I think, at least in part, will address what you're asking more geometrically. So what happens? Also, what happens on what's the situation on phase space? I mean, what does it mean? I mean, how do I also continue formulating the dynamics? And we'll just see in a moment, for example, what it means for the Hamiltonian of the system. Oops, am I doing something wrong? Yes, I am. Okay. Yeah. More or less, everything's visible. Now, what I'll zoom in on is a particular case of constraints, a subclass, which are so-called first-class constraints, because they are directly associated with systems with gauge freedom. There are also second-class constraints, which we are not going to discuss, although they also appear in many actual applications. So let me define, first of all, what the subclass of systems. So a Hamiltonian system with M constraints. We've learned what constraints are. Phi, let me continue to call them phi A, of Q and P equals 0. It is called first class, or of first class, if, well, firstly, if phi A, Poisson bracket, with phi B, where this now runs through all the constraints you have, is equal to FAB C phi C. So these are Poisson brackets, and they say, I mean, these are just phase space functions. So I know how to compute their Poisson brackets. And what I'm testing here is whether the result of this calculation gives me something that is, again, proportional to a constraint, with some coefficients which could be constants. They may also depend on Q and P themselves. So that could also be a phase space function. But this is the requirement for a system to be called first class. And we look into the geometric meaning of what that entails right now. So these, as I said, they needn't be constants. So that's not strictly necessary. If they are, then these would form a Lie algebra, essentially. And if, okay, there's another condition that concerns the Hamiltonian of the system. The Hamiltonian, of course, being another phase space function. Now, if I look at the Poisson brackets of the Hamiltonian with each one of the constraints, again, this should result into an expression that is also linear in these constraints again. So that's the Hamiltonian of the system. And these, again, these needn't be constants. Could also be phase-space dependent, these DABs. Now, yes, there's a question?
So in this particular example, how do you even go to the Hamiltonian to verify that?
There is an ambiguity, which I'll just tell you what is. Now, let me call this here condition star, I think for later usage, and this condition, let me call it double star.
Do the D's have to be constant?
No, no. These needn't be constants either, these D's. Oops. So those needn't be constant and those D's neither. Yeah.
If those are allowed to become functions as well,
Yeah.
I don't see how we cannot write it in this form. Can we just divide by phi c and then multiply by phi c and absorb it into F?
How it can not be in this form? No, well, it clearly, yeah, I'm not sure. No, it clearly, no, it's not a trivial. It's not a trivial statement. No, a linear.
Constant be anything divided by phi b, and then it's fine. We can always write it like that, unless you are reconsidering that phi b equals to 0, and you don't divide by.
Yeah, but this is, of course, exactly, I'm interested, of course, in the subspace where these phi b's will be 0. So, as a matter of fact, now, on the joint surface where all of these vanish, so in finite dimension, we can always show that if kind of the right-hand side of a Poisson bracket vanishes on that surface, then it must be a linear combination of these constraints. So it is indeed a non-trivial. Indeed a non-trivial statement. Let me introduce one more piece of notation. Just a sec. That is also very frequently used in the situation, which are, physicists' equality signs, and they mean, in this specific context, equality on the constrained surface. So this means equality on S C. So, for example, this I can write, this condition, with this convention, I could write as phi A, phi B, and says is weakly equal to 0. So that means all the same. It's equal to 0. Because the right-hand side here is 0 because it's a linear combination of the constraints, and the constraint is what, of course, exactly is what vanishes on the constrained surface. Now, so what are the consequences of this? Well, obviously one consequence is that we are reduced to the submanifold of phase space. That's kind of the obvious thing. But there is one other consequence, which we'll get to in a second, which will tell us that the action of these first class constraints, they generate kind of, they can be thought of as generators of flows on this constrained surface, where when I integrate these flow lines, they correspond to gauge orbits along which nothing changes. I mean, the physics doesn't change, so it's this kind of the redundancy we've already met in our discussions of gravity. Now, how to get there? What are the physical consequences? Well, one immediate thing is now, people have already asked about the Hamiltonian. So the Hamiltonian in these situations on the constrained surface, I mean, all dynamics, of course, all dynamics I'm interested in takes place on this constrained surface. But the Hamiltonian is not unique because you can always a multiple of the constraints to the Hamiltonian. So let's have a look at how this works. It's not unique in this situation. So we have a whole collection of Hamiltonians. Well, let me generically call them H star. I mean, it's not a single one, but anything of the form H, kind of what I get originally, Cm from the Legendre transformation, plus Cm of Qp phi m of Qp is equally good because it coincides on the constraint surface. It just takes the same values. However, well, this gives just 0, if you like, to the value of H or H star, but it does contribute to the equations of motion. Now, why is that? The equations of motion, recall, are given by taking Poisson brackets, say, of Q and H. Now, this term, am I writing this down? Yes, I'm writing it down here. So let's consider the time derivative of some phase space function G. By definition, that is just given by G with H. Now let's take this most general Hamiltonian H star. I get various contributions. I get kind of the GH from this first term here. And I get two other contributions. One where I have a Cm, and the Poisson brackets are taken with a phi m, plus, just by Leibniz rule, phi m, and G with Cm. This is, of course, so because, well, this is a general phase-space function, this coefficient, this bunch of coefficients. So I get these two contributions. Now, this is, again, this vanishes on the constraint surface. So this doesn't give me a contribution. Right? So this vanishes on the constraint surface. Let me use my new wiggly equality sign. But there's no reason for this to vanish. You see? So in particular, if I now look, say, at the time derivatives of my fundamental, kind of my basic variables, the q's and the p's, that is equal on the constraint surface to del h by del pi plus Cm del phi m by del pi. And similarly, the time derivative of pi gets also non-trivial contribution from these terms. So it has a usual minus del h by del qi minus Cm del phi m by del qi. And this is positively bizarre because you would say, look, I mean, for each choice of the CMs, I seem to be getting a different evolution. So does that mean, I mean, my evolution is no longer uniquely defined? So here, so that's what one immediately deduces. The equations of motion contain, somewhat worryingly, m arbitrary phase space functions. Exactly these Cm. Now, it turns out that one can make sense of this in a consistent manner by imposing certain other demands on the Hamiltonian and the phi's, and which are exactly these first class conditions. So let us see how this works. So the consistency, various ways of expressing this. First of all, I mean, the Hamiltonian must be such that it doesn't, I mean, of course, now the Hamiltonian, that's the usual way of solving the classical dynamical problem. I look at the Hamiltonian vector field associated with the Hamiltonian, and I integrate it up, and this just will give me the trajectories in phase space that solve the problem I'm looking for. Now, what you want to hear in the presence of these additional constraints for consistency is that the trajectories should all stay within that constrained surface. So the constraints must be preserved during, under time evolution. And of course, the time evolution involves the Hamiltonian, so this is a condition that explicitly will refer to age. Now, what is this condition? This is the time dependence of the constraint. And what I'm asking for is that when I'm on the constrained surface, then, well, this shouldn't change. So it should at most be, again, equal to a linear combination of the constraints. So that is just the same as saying phi m h. And now I'm using again completely the most general form of the Hamiltonian, so this h star, to compute my evolution, plus Cn phi m Poisson brackets with phi n should be equal to 0. Because this other, the third term was, of course, of this type, and we have already seen that that's vanishing. That doesn't give me any constraint. Now, this here, of course, by my assumption of first-class constraints, the 1 star equation here, this, of course, does vanish. And you see, this also vanishes by virtue of the second condition here. So these two conditions certainly make sure that this consistency requirement is satisfied. So this is also equal to 0. I did have a picture. Yes, there will be one more picture in a second. Now, what I also want to point out to you, and a little bit of geometric intuition, there are two ways of reading this equation of weakly vanishing Poisson brackets of such a constraint with the Hamiltonian. So what are the two ways of looking at this? Well, first of all, it's, if we now remember also the definition of these Poisson brackets in terms of the partial derivatives, this is, of course, if I think of an object that is a free slot, Poisson bracket with the h, that will just give me the Hamiltonian vector field associated with h. So this is kind of the direction of the flow lines, the ones I want to integrate up. to understand what the time evolution is. So and then of course it acts on a phase space function. And saying this means if I walk along the directions of these phi m's, of the Hamiltonian, I am staying on the constrained surface. So the flow of the Hamiltonian stays on my constrained surface. And the kind of computation, the way to write this is then to say, okay, let me just substitute in that imagine I'm sitting in local kind of standard canonical coordinates Q and P. Then I get a sum here minus del H del Qi d by dpi plus del H del Pi d by dQi acting on phi m. That is just one suggestive way of writing it. I could stick the phi in here, but of course it's the same definition. But this is just to say, look, this here is actually the Hamiltonian vector field, or rather minus it, associated with the Hamiltonian, which are called X, capital X, associated with I, acting on psi m. And this I require to be equal to 0. But there's, of course, a kind of a complementary way of thinking about this construction, which is the following, namely to look at kind of the flow that is generated by these constraints themselves. Now, what does that do? Conversely, well, going along, if I now rewrite this and kind of leave the phi dependence inside this bracket and pull out the H dependence, then I can read it as the Hamiltonian vector field associated with each one of these constraints leaves H unaffected. And saying that is, of course, the statement of the physics stays the same if I walk along the integral lines of these phi's, at least on the constrained surface. That's, of course, all that interests us. Okay, so H is unchanged when moving along the Hamiltonian vector field, or in the direction of the Hamiltonian vector field, associated with a constraint phi m, which is my notation here, as I introduced earlier, on this constrained surface. And you can then just write it in this suggestive manner as, well, the same Poisson brackets I had down there. This is equal to sum over I d partial phi m, partial derivative with respect to Qi, d by dpi minus del phi m del pi d by dqi, and all of that applied on H. And this I can just write as x phi m, now with a plus sign instead of a minus sign, applied on the phase space function H, vanishes. Oops. And this is, of course, exactly the statement of, gauge invariance of the dynamics. So the directions along which this vector, each of the vector fields x corresponding to the phase space functions phi m points are directions in which the Hamiltonian doesn't change. So they correspond all to equivalent physics. So that's what I mean by writing this. So this is a gauge direction. So the physics doesn't depend on the associated kind of coordinate. Let us look at a very simple example of this for illustration. Now let's imagine we have a single constraint phi equal to P3. So the P3, the momentum P3 of my system has to vanish. That's a single constraint, and well, and it has an associated vector field xp3, which is minus d by dq3. Now remember the definition of the Hamiltonian vector field. You take the Poisson bracket and you stick it into one of the slots, and of course what remains then is a kind of a vector field. Now what follows kind of from this condition that it should Poisson commute with the classical Hamiltonian is that d by dq3 of H should vanish on the constrained surface. So let me draw a little picture here. So schematically, let this big box be my original phase space S. Now, I have a constraint which confines me to a hypersurface of codimension 1. Let it be this thing here. And is given, of course, by P3 equal to 0. Right? That's what this hypersurface is. Now, the statement is that on the constrained surface, these constraints themselves generate a non-trivial flow. And the flow is exactly along the direction of Q3 or minus Q3. Right? So let this direction be kind of here perpendicular to the blackboard, say. So these are, say, the lines in the direction d by d Q3. Right? And what it tells me is, if this is a first-class system by definition, is that if I walk along these flow lines, if I integrate them up on the constrained surface, physics doesn't change. So these Q3s are a gauge direction. How is that, of course, expressed functionally for the Hamiltonian? What is the condition here? Well, the Hamiltonian function should not depend on that coordinate Q3. And of course, if that is the case, de facto, what I might do is, without losing any physics, I might confine myself to, yet another subspace of this constrained surface, which cuts each of these orbits once and only once. So, well, it's all very, very simple in this example. For example, the condition Q3 equal to 0 or any other constant would serve that purpose. Q3 clearly will not depend anywhere, so the Hamiltonian doesn't depend on it, so it's just floating around as a redundant variable, and that you can just easily fix, by just setting it to 0 or some other constant. It doesn't matter. Okay. In this way, what one gets here, so this surface here, this orange, well, this surface is SC. The surface that is obtained by imposing an additional gauge condition is called the physical phase space. So that has one dimension less. Right? If this original thing was 2n dimensional, this was 2n minus 1 dimensional. This will be now 2n minus 2 dimensional. And the beauty and charm of it is that this would be, again, a phase space with pairs of coordinates. And now, in this very simple example, what has happened is that the coordinate pair Q3, P3 has simply dropped from the description. Okay. Now, generally, it will always be like this locally, say when you have a system of first-class constraints. You can always arrange locally your coordinates in phase space such that you can write all these phi's as some momentum direction, which then drops out, and the canonically conjugate variable, the corresponding QA, is then the redundant variable, which you can throw out or gauge fix. Unfortunately, it's usually not possible to do this globally. So you may have such nice rearrangements in terms of coordinate transformations locally that neatly separate your directions into gauge and rest. But in general, this is either ambiguous or it just works only locally. And that gives rise to a lot of additional complications in the theory. So this is a physical phase space. Yeah. And that brings me to the end of today's lecture. Thank you.